Hello everyone, welcome to our M4 Practice Hackathon presentation. Today we're walking you through our loan default prediction classifier. Our overarching business objective was to maximize the F1 score to accurately identify risky loans without rejecting too many profitable customers.
Exactly. Predicting loan default is a high-stakes balancing act. We need a model that is both highly predictive and well-fitted to generalize on unseen data. Today, we will discuss the advanced feature engineering we applied, how we tackled class imbalance, the models we compared, and how we assess our model's fit using cross-validation and diagnostic curves.
First, let's talk about feature engineering. We didn't just use the raw data, we created new features that make business sense. For example, we calculated the income to loan ratio. We also used the log transformation on income and loan amounts. This helped us handle crazy extreme values like billionaires applying for small loans.
Right, and once our data was rich and clean, we compared several models. We looked at three main models. The first one is the logistical regression. It's our interpretable baseline, and it gives us a decent starting point, but struggle to capture complex and non-linear relationship. And the second one is the light GBM. This one is fast and highly efficient with large datasets. It natively handles categorical variables, which is great for our dataset. And the last one is the cat boost. This one is absolutely the king of categorical features, and it provides the most robust performance, but was slightly slower to train.
Next is the class imbalance problem. In our data, safe loans are way more common than defaults. We thought about using SMOTE to create fake default data, but it made our tree models overfit. Instead, we used a simpler trick, class weighting. We simply told Light GBM and Cat Boost to pay more attention to the default cases. This worked perfectly.
And instead of just picking one, we actually combined them. We created a ensemble model, we tested many different combinations and found a golden ratio, like we showed here. Our final prediction was made of 46.5% light GBM, 38.5% cat boost, and also 15% of XGB boost. And this combination easily beat any single model.
Now, getting a high score is great, but how do we know our model is well fitted and not just memorizing the training data? We completely avoided a simple train test split. Instead, we used five-fold stratified cross-validation. This ensured that the proportion of defaults remained identical across all folds.
So if you look at our learning curve, so you can see the training line and the validation line are very close to each other. This means our model is well fitted and it is not overfitting or underfitting.
Let's talk business implications using our confusion matrix and precision recall curve. In lending, a false positive means we lose out on the interest revenue from a good customer, but a false negative is much worse. It means we give money to someone who don't pay back.
And because of this asymmetric risk and because the F1 score is highly sensitive to the decision boundary, we didn't settle for the default 0.5 probability threshold. We swept through 999 different thresholds using our precision recall curve. We found that shifting our curving threshold to 0.654 mathematically maximized our F1 score on the validation set. And this adjustment perfectly balanced our precision and recall, ensuring we minimize catastrophic financial losses while maintaining a healthy approval rate.
So lastly, if we had more time and resources, we would definitely look outside this provided dataset. Credit behavior doesn't happen in a vacuum. We would bring in macroeconomic datasets like the current federal interest rate, national unemployment rate, or inflation indices. We'd also love to pull in deeper credit bureau data like the number of recent hard credit inquiries to give the model a real-time pulse on the applicant's financial stress.
So finally, if we're deploying this to production, model monitoring is critical. We would set up a pipeline to detect data drift. For instance, tracking the population stability index of our input features, or if the distribution of person income suddenly drops due to an economic downturn, our model's predictions might become overly optimistic, so we would implement automated triggers to retrain the model on fresh data whenever the drift exceeds a certain threshold.
In short, good feature engineering, class weighting, and model ensembling gave us a very strong classifier. Thank you for listening.
Thank you.